Jason, what's a qubit?
A quantum bit, which doesn't help in the explanation.
Yes.
Basically, it is when you're talking about a quantum field, you no longer just have a 1 and a 0. You also have this other thing, which is a superposition, which you don't know what the number actually is till you take the measurement and everything kind of starts to collapse from there. Yep. Interesting property of quantum physics, of which I'm not sure there's too many people in the world who have a full, true understanding of how to grasp that in their head.
Yeah.
Not only, Tim, what is a qubit, but did you know that there's many types of qubits?
Yeah, that was going to be my next question. So we just count the number of qubits, right? And we're done? How many qubits? 51 qubits is better than 50, right?
It's the problem is that numbers of qubits, you really have to categorize the qubit to understand what you're getting.
There's different kinds of qubits and they mean different things.
And there's an arms race. In other words, I would propose the title of this episode being The Qubit Arms Race and the RSA Endgame. Okay, so there is a difference fundamentally of physical versus logical qubits. And that's something that we're going to have to wrap our minds and tongues around in 2026. Because what we saw at the end of 2025 was the advent of logical qubits that were a heck of a lot more stable.
Sure.
Than...
Which isn't surprising, though I would wonder, is a logical qubit really equivalent to a physical qubit?
It's way, way, way... This is my scientific explanation. Way, way, way more stable.
Sure. Does it calculate equivalently?
The problem is that what it might do is people forget in AI, we have this concept that we call one-shotting, which is the ultimate form of, like, for the average user, they're only going to ask their question once to an AI, and they're not going to make AI think harder and harder and harder the way that experienced AI users do.
Right.
And the typical user will one-shot their question, and if the answer is not sufficient, they'll walk away disappointed. Okay. Let's say you're trying to calculate a large prime number, i.e. Shor's algorithm.
Sure.
Okay. You might require, with logical qubits, many, 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 many shots.
Okay.
Your chance of doing it one shot or much fewer shots is much higher with a logical qubit.
So maybe that's fine, right? I mean, depending on how many is many, if I could get to the number of qubits I want with logical qubits and I can at least start doing the work, maybe I can let something sit and crunch on a problem until it gets an answer. Maybe that's perfectly fine.
There's so much noise and error handling required with physical qubits that I think many people have argued they're not usable. For Shor's algorithm, for sure.
Right.
And to be more accurate, you probably will not be using physical qubits to solve Shor's algorithm for the purposes of building a cryptographically relevant quantum computer. You're probably going to be using logical qubits. Sure. So let's discuss 3 different kinds of logical qubits. Okay. So we've got the real speed demon one. Okay, I'm trying to keep this fun, right? I'm way oversimplifying. The superconducting qubits.
Okay.
IBM and Google.
Okay.
Whenever you hear about IBM and Google's quantum computers, they're like the race cars of the quantum world.
Yeah, that's your Lambo.
The problem is, though, they're closer to being logical. They are logical qubits. They're closer to being like physical qubits in that you still need thousands of them, thousands of physical qubits in order to get to the one logical qubit that we're talking about here. And so therefore the relationship is still, you're going to need many, many, many of these speed demon superconducting qubits.
Okay.
They're fast, but you need more of them.
Okay.
The trapped ion qubits, I would call that the precision play, if you will. So ion Q and quantinuum, those folks really, they have a more precise. So if you think about efficiency of the number of qubits you need, if you need 1,000 to 1 for superconducting qubits, you only need like perhaps 20 to 1. for these ion trapped qubits. And so if we only need 4,000 logical qubits to break RSA, I remember I said logical qubits to break RSA, the trapped ion path will get us there with only 100,000 physical qubits that are trapped ion. Okay. And compare that to the need of maybe 20 million for superconducting qubits.
Got it.
The IBM Google
Okay.
solution. Now, the most controversial one is the topological qubit. And do you happen to know who came up with that? I'll give you the answer.
Yes, give me the answer. I don't think
That's
I know.
Microsoft's billion-dollar bet.
Okay.
And these are like, remember the margarine?
Yeah.
The Margarana chip?
Yes.
So the Margarana fermion is I don't fully understand it, but I'm going to repeat the words that I've heard other really smart people say. It's a particle that is also its own antiparticle. And what you get when you have both sides of that is ultimate stability. That is a 1-to-1 ratio.
Okay.
So let's say you're trying to, what's an analogy? Stability wise, you know how hard it is to take a pin and balance something on a pin.
Sure.
Okay. Well, these other ones are like balancing something on a pin. Whereas a topological qubit is more like tying a knot in a rope. It's stable.
Okay.
Right?
Okay.
And so therefore, how do you undo a braid in a rope? Well, you don't just shake it and it breaks. It's very, 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 very stable. You actually physically have to you got to do an action to undo that knot. So that's very interesting. So this is the reason I say this, Tim, and this is where I'm going to land, and then we can end the podcast. If Microsoft succeeds, do you remember when I asked Michaela Mosca, what do you think is going to be the eureka moment that might get us to Z date, Q date, more ahead of time than we thought? Yeah. And he specifically said, ultimately, it'll come down to highly, highly stable qubits. Yeah. If we break that problem, that's the eureka moment that even he couldn't predict. And I think that the topological qubit concept, which a lot of people are like, it's impossible, never happened. The Margarana fermion is like a dream. Okay. I'm not arguing that. But what I'm saying is this, that could be the black swan where we all go, whoa, maybe RSA can be broken in 4,000 topological qubits.
Oh, okay.
And that's, I mean, like, throw eggs at your screen. Feel free. I'm not promoting that this is going to happen.
You're the one who's going to have to clean it. Go ahead and throw anything you want at your screen.
But I think, Tim, we're so far along in quantum computing now that in 2026, I think it's important to start understanding the distinction between these types. Because there is a third type out of three. One of them's kind of a dream, but there is a company putting billions of dollars on the bet that this is real. And if it is, Tim, it's going to affect our lives.
Yeah, sure will. Yeah. And it's that's, I mean, I think it's a good nuanced view of this thing to say, not only are we trying to build more stable qubits, but we're also trying to figure out the best approach to building stable qubits.
I don't blame all these big, truly gigantic trillion-dollar market cap companies who are probably working alongside nation states very much so to build these types of systems. And it'll be humanity-wide importance of what comes out of this. And I'm just saying that, okay, we're on the path to Shor's algorithm on all of these. It's just that there could be a eureka moment in one of them that could take us there quicker.
Yeah.
And I just wanted to be a little more precise in how to say it. And I think this episode explains it.
Cool. Excellent. Thanks, Jay.
Thanks, Tim.